Okay, now let's do an example of Young's double slit experiment. Let's do example 5.3.1. Okay, now a double slit experiment is conducted using a 450 nanometer light. So we have our wavelength here and two narrow slits which are 0.5 millimeter apart. And we have our D, which is the distance between two slits. Find the angle, the theta, when the fringe is found at the third order maximum. Now, still remember what I've taught you before. For maximum, starts from 1. Okay, so if it wants the third order of maximum, your M would be 3. Okay, now B, they want the second order minimum from the central maximum. So minimum is for destructive interference, maximum is for constructive interference. So the second order minimum or the second order dark fringe or the second order destructive interference, okay, starts from 0. So 0, 1, meaning your M is equals to 1. Okay, right now let's do A first. For constructive interference, this and theta is equals to M lambda, because they want maximum here, so we will use constructive interference equation. Okay, so we have our D here 0.5. Make sure you change everything to SI unit. Sin theta, theta is the one that we need to find. Your M is equivalent to 3 and your lambda is equals to 450 nanometer. So you will get here So you get here 2.7 times 10 to the power negative 3. Okay, do not forget to bring your sign. So shift sign here, and your answer will be 0.15 degree. Okay, now for B, the second order minimum from the central maximum. So minimum means we have to use destructive interference equation. D sin theta is equals to M plus half lambda. Right, so put in all the values. 0.5 times 10 to the power negative 3 sin theta. Theta is the one that we need to find. Your M just now was 1 plus half times your lambda 450 nanometer. Okay, so you will get here. I will immediately calculate this. And you will get 0.077 or equivalent to 0.08 degree. Okay, now let's try. Now let's look at another equation. Just now I've given you two equations. First for constructive interference, the second equation is for the destructive interference. Now the third equation is to find the position of the fringes. For example, if let's say I want the distance between the 0 order bright fringe to the 5th order bright fringe. So the distance here is labeled as X. Okay, and to find X, we have the equation of X bright is equals to M lambda L over D, or if it's for dark bands or for minimum or for minima or for destructive interference, we have X dark is equals to M plus half lambda L over D. So these are the two equations that you need to use to find the distance between fringes. If let's say you want to simplify the equation, I'm going to show you back, okay, what I've mentioned before, the distance between the 0th order to the 5th order dark fringe, bright fringe. Okay, so I can either solve it like this. Okay, X at the 5th bright fringe from the center minus the 0 fringe, or there's another easy way. You can just simply use lambda L over D. This is to find the spacing between two bright or two dark fringes. Right? Okay, let's do an example here of distance between fringes. A screen containing two slits 0.1 millimeter apart is 1.2 meter from the viewing screen. Okay, I forgot to mention just now, there's another L stands for the distance between the slits towards the viewing screen. Okay, so we have to know our D, distance between slit, our L, the distance between slit and the screen, our X, which is the distance between fringes. Okay, now the screen containing two slits 0.1 millimeter apart. Right, so this will be our D because it's the distance between the two slits, is 1.2 meter from the viewing screen. This will be your L. Light of veiling lambda is equals to 500 nanometer falls on the slit from a distant source. Approximately how far apart will adjacent bright interference fringe? So there are one bright fringes. Adjacent means between one to another fringe can be seen on the screen. You can either choose any fringes that you want, provided that it is adjacent towards each other. So the easiest will be the first and the second fringe, at the first order and the second order, right? So like I've mentioned before, you can use the easier equation, which is lambda L over D, to find the distance between the two adjacent fringes. So delta X is equals to lambda L over D. Lambda will be 500 nanometer, okay, times the distance between the screen and the slit, which is 1.2 meter, divided by the distance between two slits, 0.1 times 10 to the power negative 3, or 0.1 millimeter. So you will get here 500 to the negative 9 times 1.2 divided by 0.1 exponent negative 3. You will get here the distance between the two adjacent fringes is 6 times 10 to the power negative 3 meter, or 6 millimeter. Okay, so this is one method. Another method is you can find it one by one. X2 is equals to m lambda L over D. So your X2 second order times the wavelength and the distance between the screen and the slit, divide by the distance between two slits. You will get here 2 times 500 nanometer times 1.2 divided by 0.1 millimeter, and you get 0.012. So let's calculate at the first fringe here. 1 times 500 nanometer times the length, or the distance between the screen towards the screen, the screen to the slit, and 0.1 times 10 to the power negative 3 here. You will get here 6 times 10 to the power of negative 3. So minus these two, lambda x is equals to x2 minus x1. So 0.012 minus 6 times 10 to the power negative 3, and you will get 6 times 10 to the power of negative 3. So you can use either this method or this method, or if you need to check your answers, you can calculate both. You should get the same answer. Okay. Right, so I will need you to do this example. Okay, the answers are there for you to check, as well as these examples. If let's say you don't understand the question or you cannot solve it according to the answers given, you can just refer to your lecturers for the answer scheme or for you to check the answers. Okay.